Yeah, thank you guys. Thanks, John, and thanks everyone for joining. Happy New Year. I hope everyone has a great 2025. So I'm excited to go over this information with everyone and expose you to this technology that's been around for a while. And John's definitely an expert and can talk through a lot of applications. So please ask questions. And John and I would be happy to answer. If you don't know, Sierra Circuits has been in business, and we are a PCB manufacturing company and assembly company, and we're located in the Bay Area. So we focus on a lot of the mil-aero, industrial, medical markets. Those are our three big markets, and we do a lot of complicated circuit boards, hence the topic of today, where people are trying they realize their board is more than just a board, and they're working on difficult problems to solve. So first we're going to answer the question, why should you consider embedded resistors and capacitors, and then how to be a little bit more educated about going through that process, and some design guides for that. And again, John's really an expert, so you should ask as many questions as possible and get the most out of this webinar. So again, the big question as to why. So, if you have a board or a technology challenge, that's really when you should be considering embedded resistors and capacitors. So it replaces surface mount devices, and that means that you would have less solder joints to worry about. And if there's a lot of exposure to external forces, that could be a very good way to reduce risk of mechanical failures. And then also you can use this technology to shrink your electronics and also achieve an overall better signal integrity. So there are some very key advantages to this technology if you're facing any of these challenges. So again, it ultimately depends upon your application, and taking a look at some of the kind of decision factors we've outlined this chart. If you're price conscious, and you can't offset some of the cost, then maybe it's not the way to go. But if you can offset the cost and you can justify it, and you're also getting benefit in terms of performance, then I think it's definitely worth it. So these are some of the considerations that you need to when you're selecting embedded resistors. So you want to think about the resistance and the tolerance that you're looking for. So choosing values that you want to maintain consistent impedance throughout the circuit. And then you also want to be able to modify the length or width of the resistor to adjust the resistance value. And you want to verify that all of this aligns with your PCB manufacturer's capabilities, and it fits your stack up. So we'll be going over that. So in terms of the next factor of power dissipation and current capacity, so you want to ensure that the resistor's power rating is high enough to handle the calculated power dissipation. And you always want to select a resistor with a power rating that provides a safety margin above your requirements. And this will help with your long-term reliability. And then another important factor is the coefficient of resistance. This is a quick chart that showcases that. The TCR will indicate how much of a resistance value changes with the temperature fluctuations, and it's measured in parts per million per degree Celsius. Okay. So you want to aim for TCR values below 100 parts per million degrees Celsius. In terms of the types of embedded resistors, with their pros and cons, we've also created a chart here. So for high power or high voltage designs, you want to go with a thick film resistor. And you want to pick thin film resistors for more precision and stability. And there's also an option of plated resistors for high current and high frequency applications. So I'll let John go through those in detail in his slides. So some other tips, always to select your embedded capacitors, always select a capacitor with a voltage rating 20 to 50% higher than the maximum expected voltage in your circuit. You can use ceramic capacitors in the range of 0.01 to 0.1 microfarads. And for RF filters, you can select capacitors between 1 and 100 nanofarads. Some design guide pointers. So when selecting the materials for high frequency and RF applications, you obviously want to choose materials with stable dielectric constants. And for high frequency circuit boards, you want to use materials with a dielectric constant between 3.5 and 4.5. And you want to choose materials with low dissipation factors, preferably below 0.005, to help with your signal loss. In terms of stack-up design tips in general, you want to allocate specific internal layers for embedded resistors and capacitors. And then, you do that intelligently, and you want to ensure that your stack-up is symmetrical, that you have good copper pour, and then you're positioning your embedded components as close as possible to the signal layers to get the best signal performance out of using this technology. So, again, there's always good advice that we have on achieving good signal performance or achieving a uniform impedance across the line. So some points are you want to modify the trace width and clearances to match the desired impedances. You don't want to place the embedded components directly beneath critical high-speed traces unless they're part of the impedance matching network, and perform the TDR measurements on prototypes to verify the impedance. And this technique will help, solve any inconsistencies that you see across the PCB. So we're going to do a quick demo of our impedance calculator, as we find it's a very valuable and popular tool among the engineers.
Hi everyone. So we have Sierra Circuit's impedance calculator here, which uses the 2D numerical solution of Maxwell's equations for PCB transmission lines and renders fairly accurate results that are suitable for circuit board manufacturing and engineering analysis. The impedance calculator tool supports 82 impedance models with multiple geometries. As we can see here, we have the uncoated, coated, and embedded microstrip, as well as the strip line. And each of these structures, uh, uh, with each specific model, you can choose them in a single-ended differential pair, coplanar, and etc. Let's go with a coated microstrip for now in a differential pair. Uh, and we can see that the simple and the composite models are also available here. Let's go with the simple model here. Our impedance tool is integrated with the signal loss, crosstalk, and the S parameter calculator as well. I will be showing it to you in a while. Uh, we also have different units over here in the tool that you can use for the calculations. And you can choose the desired unit system. I'm sorry about this. I think there's a slight delay.
Well, that's a fail. You know what, Vandana? That's okay. I can send everyone the link to the demo in the thank you.
Yeah, sure.
Okay. Thank you so much.
I'll try again. If suppose this opens, then we can do the demo again.
Okay.
Yeah, let us know. We'll include you into the demo. Okay, I just have a couple more slides before I pass it over to John. So some thermal management strategies you definitely need to think about, thermal relief, and so you want to position your embedded passives away from heat generating components. You want to add thermal vias as good general practice. Copper pores are also good to distribute heat. And you can, of course, use heat sinks, which is a very common practice. So, in terms of the fab notes, of course, you need to mention this on your fab drawing if this is a direction you want to go. And so just like specifying impedance on your drawing, you need to make sure that you've specified it completely. So these are some of the key points when you're putting it on your fab drawing on how to specify it so that the fabricator is well aware of what you're trying to accomplish. And if I haven't stressed it enough, the fabricator that you choose should have experience with, building these type of layers into your stack up. And it does require some attention, although not too bad. It does require some attention and process changes. So you should talk to your fabricator and kind of alert them ahead of time. So that's all I had. I'll pass over to John.
Again, thank you to Sierra Circuits for inviting me to talk today. I really appreciate it. And so for those of you who I've been in the industry for a long time, so many of you might know me, but if you don't, I've been in the industry for 40 years. Currently the director of business development for Quantic Ohmega-Ticer. And I've worked on both sides of both resistors and capacitors, which I'll talk to today. And concentrating mostly on what we call formed embedded passives as opposed to placed. So formed are actually where you use the PCB process to make the resistor or capacitor versus taking a discrete and putting it in a cavity inside the board. But I'll talk a little bit about that as well. So get a quick overview. Amit has already done a great job of giving you an overview. I'll just go into a few more details, a little bit more details about how things are fabricated, as well as applications. And then at the end, I have a special type of embedded capacitor that is a discrete that is actually makes it easier to be embedded in certain cases. So just a quick thing about us. We are we're called now Quantic Ohmega-Ticer. Many of you might know us as either Ohmega Technologies or Ticer Technologies. But basically now we're all part of one company. Omega's been around for a long time. The original concept dates back to the 70s. It was in '83. It was formed as its own separate company, and then in 2002, a copper fuel company called Gould created this other competing technology. And in 2006, Ticer was spun off from Gould. But then in 2021, a company called Quantic Electronics bought both companies and brought the technologies together, and that's where we are today. So if you look at our material, one of the nice things about the embedded resistor material, it's a resistor layer on a copper foil, but it's basically a blank slate. You can actually use it to do whatever you want as far as a pattern goes. You're not restricted to having it be like a rectangle or a square or something. It gives you quite a bit of design flexibility. And because you're embedded inside the circuit board, you are reducing the parasitic inductance and capacitance, because now you've basically putting it in line with the traces, and you're eliminating the vias and the solder joints and the associated problems with that. And we've been partnering with leading ODMs to develop best-in-class electronics for aerospace, defense, and consumer electronics, as well as other applications for a long time. Things that we're seeing its uses, It's because of the nature of the material, actually used as electromagnetic energy absorber. And by structuring patterns, you can basically make things like bandpass or filters, things of that type. And then also we're seeing a lot of interest now in Wilkinson power dividers because of the high frequency, and I'll get into that in a little bit. And then also can be used as a heater. You know, I kid around with people that our material can be used as a resistor, a heater, or a fuse, depending on how much power you give to it. Normally, people don't want to use it as a fuse. So, but it does have heater applications. And then also it's gaining traction in electronic packaging because of the ability to put a lot of passives in a very small space. So again, it's using standard copper foil. It's used in the industry. It's used to replace discrete resistors that are on the surface, allowing you to have better density. And again, it also can be used for heaters as well as because of its frequency selective surface characteristics, it can be used in that type of aspect as well. So it gives you better density, freeing up board space for, you can either reduce the board side or edge functionality. You have shorter electrical connections, which make better electrical performance and lower inductance and reduce EMI. At higher frequencies, a lot of these passive components can actually become, radiate EMI energy. And so without them there on the surface, it helps a lot. Again, reliability is improved because you don't have solder joints. It's stable over a very temperature and frequency range. And it also can allow you potentially for single-sided assembly because you're getting rid of some of the, if you get rid of enough passives, you can, a lot of times the passives put on the backside opposite the package because of space. If you can get rid of that double-sided assembly, there's a cost savings there. And also in some cases, like things that are going up into space or maybe on an aircraft, weight reduction is also important. Even though these resistors are typically small, when you're putting things up in space, every gram counts. So we can see a benefit there. The two types of material, we start off with your general class 3 copper foil. It's electrodeposited copper foil that's used to make, it's a regular everyday PCB type copper foils. And then we either go ahead and plate a nickel phosphorus on top of it on the rough side, the side that's going to go against the laminate. And that's done in our Culver City, California facility. And that's the old, Omega Technologies company. And we work with all the major CCL, copper clad laminate suppliers. And then the other side of it is the Ticer material, and that is a sputtered material. And there we use nickel chrome aluminum silicate, or chrome silicon oxide. So 3 different targets we could use. Over 90% is the nickel chrome, because the other two are used for very high resistance numbers. Again, a lot of same customer base. Over time, they developed a little bit different applications. So so Panasonic might use more TCR than Omega and things of that type. But we basically work with all the laminators. And we have our major facility for sputtering is in Windsor, Connecticut. And then the finishing operation where we actually will go ahead and put like a adhesion promoter on the copper and cut it to size for the customers is in Chandler, Arizona. And we can go on rigid flex materials or rigid flex. So it's because the nature of the material, it can pretty much lend itself to any type of substrate. And you talked about resistance before, Amit, and we kind of simplified it because we would do ohms per square, which is a dimensionless number. So we control the actual sheet resistance by controlling the alloy and then the thickness of that alloy. So let's say in this case, we're talking about a sheet resistivity of 25 ohms per square. Well, it doesn't make a difference what size the squares are. It could be 1 meter by 1 meter or 1 millimeter by 1 millimeter. It doesn't make a difference. If it's a perfect square, you're still going to get a 25 ohm resistor. And the way we change the sheet resistivity is the thickness. So our thickest material is our 10 ohm Omega, and that is 1 micron. And so if we wanted 100 ohm per square, we just make a 1/10 of a micron. So we control the sheet resistivity by the plating thickness or the sputtering thickness in the case of Ticer. And so if you want to change the resistance value, the final resistor value, you change the length to width ratio. So if the length becomes twice the width, it becomes a 50 ohm resistor. And so that way the same sheet resistance can be used to make multiple resistors on the same plane, which gives you, again, a lot of design flexibility. And like I mentioned earlier, you can use different size, different shapes So it's not unusual to get high resistance numbers where people do a serpentine pattern. So you get a very large amount of travel in a relatively short space. The nice thing about these buried resistor materials is that they are manufactured pretty much using standard PCB processing. So when you get the laminate from the laminate supplier, the board shop it would look the same as any other laminate. What you do, though, is you basically go through your first imaging step. And the first imaging step basically will define all your traces as well as the resistors as far as the width goes. And so you'll go through your normal process. You'll develop that strip and then the material. Now, in the case of Ohmega, the nickel phosphorus is a little bit thicker and a little harder to etch with the cupric etching, the interlayer etching. So you have to go through a copper sulfate bath to remove that background etch. That's about the only thing that's special. And people are doing it every day, have a little copper sulfate bath where they use to remove the background resistor material. In the case of the Ticer, it's thin enough and the nichrome is more sensitive to the cupric. So you can typically do that in the same pass. You don't have to do an extra step. Then you strip the resist off, and now you go to put the photoresist back on. And now what you have to do is just open up a window where you want the resistors to be. And so you go ahead, if you look at that step 6, and so you would go ahead and put your photoresist down, expose, develop, and now you would etch using an ammoniacal etch. And what's nice about that is the ammoniacal etch, which is your outer layer etch in most circuit board shops, removes the copper, but it doesn't attack the resistor material. So that after you strip the resist, now you have a defined resistor pattern. And so you create that extra layer of artwork, which is basically the window that you open up to expose the resistor material. Then after that, you go through a normal oxide or oxide alternative, laminate, and put into your circuit board. Typically, people will do a test. It's typically not 100% test of resistors, but they'll do an audit, a sampling, to make sure the resistors are in the specification at this point before they would laminate it into the circuit board. So when picking your resistors, the targeted resistor you want to embed, it helps to know, you want to avoid really high value resistors because it could be very cumbersome to make inside the circuit board. So anything like 10,000 ohms or above, you have to take a look at that, whether it's possible. And also precision tolerance resistors. Right now it's so easy to buy plus or minus 1% resistors that most designers just do it as default, whether they need it or not. Well, it turns out for a lot of applications, plus or minus 15, 20% is perfectly fine. And that's typically more of what you're going to get using embedded resistors. So there are some things you can do to improve it, but for the most part, if you really do need a precision tolerance, you can either laser trim the resistors or use a typical surface mount. Then go ahead, you specify the attributes of the package footprint where you're going to put it. And typically for design flow, you would go ahead and create your resistor almost as if it's a physical entity, but you put it into your library. But then you would place it then on that layer. But it's just your imaging pattern that you're doing. And then you also have to consider the tolerance that was mentioned earlier, the power and the tolerance. We try to tell people to make your resistors as big as possible, because that will help with both the tolerancing as well as the power handling capability. We have a calculator. Actually, we have two. We have one for the Ohmega and one for the Ticer, because they are slightly different because of the different types of materials and the thickness. But if you could sign up for a technical library on our website. And so what happens is you basically plug in, you can go two ways. You can either plug in the resistance you're looking for and the power rating you want and the tolerance, and you pick the ohms per square resistance material you want, and it'll come out what length and width resistor you need. That and also will give you an idea of the ESD survival level, because a number of like commercial products, you have to, they do the human body model for ESD, so you don't electronically discharge, electrical discharge, prevention, having a problem. And so, you can go that way, or if you know the length and width of your resistor, then you can go ahead and back calculate, and it'll tell you what the resistance is, as well as how much power it can handle. Typically, we're dealing in milliwatts. If you have this, I have done cases where we've gone with relatively good size resistors and done it in the watts, but most of the applications people use our material for is in the milliwatts. So some of the applications, we're seeing a lot more in things where there's tight spaces. like packaging or interposers, things of that type. And so, again, you can eliminate the solder joints and get better, you can put the either inline with the traces or put them underneath. So it gives you a lot of design flexibility. It also helps with signal integrity. As you mentioned earlier, you get that inductive loop out of there. And so the resistors are essentially in line with the traces. And so you get much better, signal performance. Really driving a lot of the growth is in the RF microwave world. With now that we're, especially with 5G and other technology, people are going to phased array antennas, and basically these are the ones that use beam steering as opposed to actually having something rotate. They would actually, or have multiple ones. They would have one that can do beam steering, and so they need a lot of things like Wilkinson power dividers and resistors. And the Wilkinson power dividers typically have discrete resistors. Would be on these gaps, as you can see, where the gray line is, that's our resistor material. Normally that would be a discrete resistor that would have to bridge that gap, and so you have to solder it, and then if you want to bury this thing, you have to create cavities for those resistors. Now with our material, it's in line, and so not only do you get much better, it's a lot easier to process and make your power dividers. It also helps with high frequency performance, again, because of the same reasons of getting rid of those solder joints and also the transitions. High frequency materials do not like metal transitions. So if you can go right from the copper to resistor back to copper, it makes it a much better performance. We just recently built a attenuator, which is used quite a bit in the RF microwave world. We did it in conjunction with our sister business called X Microwave. And they basically, they're an interesting company. They make a product that almost, I call it electrical Legos. They have a special connector technology, so they can take discrete modules and plug them all together to get very good prototyping for high performance as well as small volume production. So we work with them and an outside design company to make both a 3, 6, and 10 dB attenuators. And so what was nice about it is they were able to use our material and make basically instead of taking 3 discrete resistors that would be normally used to make an attenuator, we made a T resistor, and it basically had better performance than anything that's out on the market, according to the specialists. I am not an RF microwave expert. I'm more manufacturing and materials guy, but they basically said that it really surprised them how both the simulated and the actual performance came out to be exactly what they expected. And so we're expecting to see a lot of growth in this market. When it comes to embedded capacitors, embedded capacitor is, you form a capacitor by basically taking two, it's dielectric between two conductors in simple terms. And the things you have at your disposal are the size of the capacitor, the space between the two conductors, and the dielectric constant of the dielectric. So if you make the area bigger, the capacitance goes up. If you make the thickness thinner, the capacitance goes up. And if you raise the dielectric constant, the capacitance goes up. And so all those things go into it. Right now, the courtesy of FaradFlex, my old company, Oak Mitsui Technologies, they provide some of these slides, but there's also DuPont makes a product called Intera that is a polyimide-based thin film that goes, it's typically 1 mil and 12 micron are available. And then 3M also makes a product they call ECM, and that's used. It's a highly filled epoxy that's used to make more discrete capacitors as opposed to planar capacitors. Applications for embedded capacitance go anywhere from routers and servers, to storage, the supercomputers, and then of course military, aerospace, drones. There's a lot of applications. So the majority of the applications are planar capacitors for decoupling, but the discrete capacitors are growing for very special applications, which I'll go into a couple, like the MEMS microphone. But it is a growing market. Here's an example, or kind of an early example of using both technologies together. So inside the package that the MEMS microphone sits on is the FaradFlex material, which forms as a capacitor. Typically, they're small 20 picofarad capacitors. There's also a couple of resistors in there, and what that forms is our material. It forms an RC filter. with there's so many frequencies going on in a cell phone these days between, Bluetooth, near field, 3G, 4G, 5G, everything that's going on, there's a lot of noise around that. And so by putting this RC filter in the package, you can help improve the signal to noise ratio with the microphone and improve its performance. Also, by getting rid of the discretes, the only thing in the cavity now needs to be the MEMS microphone itself, the actual silicon MEMS device, and also the ASIC. So it makes for better acoustical performance that way as well. And so this has been a project that's gone on for quite a while, and it's used in very high-end cell phones and other types of applications where they need a high-performance microphone. The nice thing also about embedded capacitors, because their thicknesses are typically, you can buy the old 2 mil, what we call the ZBC 2000, it used to be called, or BC 2000. And a lot of people use that. It's just the 2 mil fiberglass. You get some good performance out of that versus a thicker core, but the benefits really start to pick up when you're talking about the 1 mil and below. And so you can go ahead and reduce the overall thickness of your circuit board by quite a bit by putting these layers in as opposed to the power ground. And so you can go from, like I said, 200 micron power ground down to, 25 to 12 micron. And what you can do with that is you can either make the boards thinner, which helps with your aspect ratio for plating purposes, or if you want to keep the same thickness, you can actually now use that to put additional signal layers in to help with, with your routing. So it gives you a lot of, improvement in that respect. And where this, the decoupling capacitance improvement with the embedded capacitors is right in the sweet spot in between, like, the bulk capacitance you're not going to replace. Those are your big tantalum capacitors, or, the bigger ones. But we replace a lot of the 0.1, micro, the 0.1 micro, farad type capacitor due for coupling. A lot of them go away because in the 10 to 200-300 megahertz, range, really and up to the gigahertz range, that's where the PCB gets involved with decoupling. And by putting these planes in, you can get rid of a lot of decoupling capacitors. And here's an example where you can see the old BC 2000 technology, 50 micron. There was an attempt to make a 1 mil version with fiberglass, but it never worked out. It was too hard to handle. And so these film-based ones started about 24, 25 microns and go down to as small as, currently for decoupling, the thinnest ones are 8 micron, but if you want to go to for the discretes, it goes down to 3 micron. But you can see that in the several hundred megahertz up to the gigahertz range, that you get a big improvement in the performance. With the impedance getting much better by using thinner laminates for your power ground layers. And then also there is a benefit as you go into the higher frequencies. It dampens out resonances as you get thinner, and but when you get into the inductive range, the thickness is actually more important than the actual dielectric constant, which makes so, because again, it goes into the inductive range, not the capacitance range. So the dielectric constant of the material is important for the low frequency, but for the higher frequencies, the thickness is the more important thing. And this is some simulations that were done, using we use a 24 mil spacing. And which is not uncommon when people don't put their power grounds together. You can have 24 mils between your power ground if you sneak 2 signal layers in between, which you don't recommend for power distribution, but people do that sometimes for signal integrity. But then if you took off the 580 decoupling caps of original design, it gets even noisier. But all it takes is a 1 mil plane without the decoupling caps, and then the noise goes away. So you get much better performance with that. So sometimes, though, the capacitance of these planes, like for decoupling, the planar capacitors of 1 mil are perfectly fine. But sometimes, like in the MEMS device or some of these other things, the capacitance density of these formed capacitors is not enough. So you may need to boost that. And we have a sister company called Ulix, and they just came up last couple of years with a patented type of capacitor that basically it's a they call it a gap capacitor. And what it does is it now makes it much easier to incorporate a discrete embedded capacitor. You can see the picture right there. The gap capacitor has both of its electrodes on the same side, but what you can't see inside is the actual electrodes and the dielectric. But by doing this design, It makes it really work very well at high frequencies and also get much better higher capacitance density. In fact, that's one of the most highest capacitance density products on the market. And so what happens is you get, much better performance both for high frequency and for capacitance density. And this can be thinned down to as little as typically it runs about 125 microns in thickness, but it can be thinned down even more so for embedding. And this is just an example. This is with the help of our buddies at Monolithics. They modeled the technology and they showed very good high frequency performance. So if you do need that boost in capacitance that formed capacitors can't accomplish, we can do it with a gap capacitor. So in summary, Ohmega and Ticer, now one company, and we could use the right technology for the right application. Embedded resistors lead to improved electrical performance, reliability, and space and weight savings. There's really a lot of benefits to it. And by using embedded capacitors, you dramatically decrease the need for discrete surface mount caps, improve power distribution, signal integrity, and you can reduce the board size or thickness. And embedded resistors and capacitors are manufactured using traditional PCB processing. So companies like Sierra Circuits and other leading PCB fabricators worldwide are making this product every day. So the risk factor of using this technology is very low because both technologies have been around for a long time, have been proven. They're actually used in mission-critical, high-performance applications. And so there should be a very high comfort factor with using them. We have design tools. Again, Sierra has some design tools. We have design tools to help people go through for their first-time use. We like to handhold people through the first-time use to understand their application and what's the best use of the material and how it can be manufactured. And again, if you need higher capacitance requirements, we also have a capacitor for that. If you want to embed something in the board using our gap capacitors from Ulix. And again, I'd like to, let's see. Yeah, and so here's contact information. Again, I'm John Andresakis. Bob Carter and John Ranieri are from Oak Mitsui Technologies, and they do the FaradFlex product. And then Todd is in charge of our Ulix capacitor. So reach out to any of them or myself with any additional questions. So, thank you for your time and attention.
Thank you so much, John. So Vandana is going to be able to do the demo on the impedance calculator. So Vandana, you can go. And while we have the demo, I'm going to ask you to answer a couple of more questions. Okay, you should see them on your screen. Thank you, Vandana. You can start.
Yeah, thank you, Lucy. And sorry, everyone, for earlier. So as I was saying, we have 82 different calculators with different models and geometries. And this is one of them. That is the coated microstrip differential pair impedance calculator. So we have the unit system here. We'll go for mils for now. Let's enter the input parameters. The dielectric height H1 is 3.348 mils for now. Let's go with a dielectric constant of 3.63. A coating height H1C of 1.5. Coating height H2C already has a default value here, but you can change it if you wish to do so. Then we have coating height H3C. Scope for 1.5, and similarly coating dielectric constant 4.2, which can be changed, of course. Then we have delta W here. Delta W is the difference between the top of the trace and the bottom of the trace. You can click on this help guide here, and you can see that there are delta W values based on the starting copper weight, and you can use that as a reference. Let's go with 0.5 mils for now. Enter trace thickness, about 1.45 mils, and a trace separation of 7 mils. I want to calculate the trace width, so I will add a target differential impedance here and click on calculate W. We will see that the trace width will be calculated and displayed along with the other parameters like the uncoated differential impedance, coupling coefficient, odd mode impedance, etc. Similarly, we have the signal loss calculator for the same model. Let's enter dissipation factor of about 0.024. The coating dissipation factor can be changed if you wish to do so. Let's go frequency of 10 gigahertz. an entire surface roughness of about 6 microns. This is a standard roughness for a foil, and a length of 2 inch. Click on calculate loss, and we can see that the signal loss output for the odd and the even mode will be calculated and displayed. Similarly, we have the S parameter and the crosstalk calculator for the same chosen model. Thank you so much.
Thank you, Vandana. Okay, John, if you can open the Q&A, you will see that we have some questions. Can you see them?
Yes.
Okay, great. You can start answering if you want. I think Amit already answered the questions for Sierra.
Okay, so you just want me to, okay, so I'll just go down the list.
Yeah, you can just read the questions and answer
Yeah.
live.
Yeah, do that. Okay, yeah. So how to design for embedded components in the PCB design, the tools. Yes, when it comes to embedded resistors, I mentioned that you have to go ahead and make basically the separate, basically create that window layer. It's an extra layer of artwork, but it works in all the different design suites. So you could use, Altium, Allegro, well, all the standard ones work. It's just learning how to use it, properly to add that additional layer. So it's really not it's not a big deal. And the circuit board shops, they're really, proficient in helping do that, and we can help it as well. Okay. I see the second answer was question. Okay. Yeah. And so the design rules for embedded resistor towards power dissipation limits and tolerances. As I mentioned, we do have the calculator that can help as far as if you go ahead and it can tell you exactly how much power. And I have to just tell people, when we do our power rating, that's where we take the resistor, we put it on the laminate, and then we do it, and we actually test it to failure in open air. So there's really no heat sinks anywhere. So it's just on the laminate surface, and then we put power to it and see where it fails. And so it's worst case scenario, because if it's embedded, you also typically have layers, copper layers above and below it, as well as the prepreg, which help absorb some of the energy. So we derate it. So we're worst scenario, plus we also derate it at least 25%. So typically can handle more power. And then also the tolerancing, like I said, depending on the size of the resistor, the material itself, we guarantee typically about, plus or minus 5%. Then you add the etch tolerance. It can easily go up to 10 to 15% overall, just on the etch tolerance. And so we see a lot of typically 15% to 20% tolerance on a lot of the designs. And yes, micro vias can be used, with this technology. There's no restrictions with that. You can you can create clearances through it. So the only thing that we do recommend is it's in our design guide. When you're drilling, when you have your pad that let's say you're connecting to a pad on a layer that has resistors, we like the resistors to be offset from the pad a certain amount, so that any heat that's generated during drilling or any mechanical stresses won't affect the resistive layer, because these are very thin layers. So they're very robust when they're inside the board, but we still want to try to minimize any heat or stress that might see it during that time. We have done some RF characterization in the embedded resistors, and we do have some things available. Like I said, the attenuator was tested up to 60 gigahertz, and we've had very good results with that. So, and we also tested the effect of the resistor material being under the traces up to like 40 to 50 gigahertz, and there's a minor impact of loss by having that resistor material underneath it. Let's see here. Yes, we worked when I was on the IPC committee for embedded resistors and capacitors, and we worked very well with UL on specifications for these materials. So yes, these products are, if you have a product that's designed with it, it does meet UL. Obviously you have to go through the normal UL testing, but these materials are UL accepted, and so there's no problem with incorporating into the resistors or capacitors. Since the resistor material is very thin, it's actually most of the resistor material we supply is on 1/2 ounce copper, although it can be supplied on 1 ounce. And so it's typically incorporated right into a signal layer. So the amount of thickness you're adding, I told you, the worst case scenarios are 10 ohm per square material, and that's like a micron. So our material really is almost a negligible thickness. Now, if you need to add an additional signal plane, it's just going to be that half-ounce copper additional thickness that you would have to add, but it doesn't add much. And in the case of the embedded capacitor, you actually reduce thickness because of the reduced spacing between the power and ground plane. Yeah, so artwork modifications for tolerancing. One thing we do is because it's a double, there's two tolerances to worry about. One is the overall resistance tolerance. The other one is the, well, two things that affect resistance tolerance. One is the control of, typically it's the width and the length of the etching, and then also registration. So since you're doing a two-step etch process, you have to allow a little bit for misregistration between the first and the second etching process artwork. You know, so people are using very precise things, these like laser direct imaging and very good registration. So you may only have a 1 mil tolerance in placement, but that has to be accounted for. So that's why, like, you may want to make the electrodes a little bit bigger than the resistor area, just to make sure that you don't have the resistor area go outside of that would affect the resistance value. And again, the bigger the better. We don't like, you know, we have people are using 5 mil wide resistors in certain applications, but that will be, you know, that will increase your tolerance. So if you can stay above, you know, 10 mils, 20 mils as a width and a length, that typically gets your tolerances, you know, much better. And the last one is if they need an 8-layer board for design to incorporate embedded passes, well, I need 10. Okay, so the thing of that is with resistors, the answer should be no, because you're basically putting the resistors, essentially, they would have been on the top anyway, and you're bringing them down. So you're not really adding an extra signal layer. You're just basically getting rid of the via and putting the resistor where it normally would be. You know, in the circuitry, it would be exactly in the same place. So there's no additional layer you would have to put. When it comes to the embedded capacitors, if your design doesn't have your power grounds together, you may have to put an additional dummy, reference plane, ground plane in, because that's how it works very effectively. So we have seen some designs actually go from, let's say, a 12 layer or a 12 layer to a 14 layer or something like that, to add that extra dummy plane in there. But because it's so thin, it doesn't add thickness. It just adds another layer or two in there in order to accomplish that. So instead of having a reference plane, signal, ground plane, you'd have like a reference plane, signal, ground plane, signal, then ground, or reference plane and ground plane, power plane, excuse me. So you have to add a couple of extra layers in there if you want to do decoupling capacitance with a planar or a capacitor. But usually the overall performance, can justify the additional layer.
Thanks. I see we have someone raising their hand. Sam, if you want to unmute yourself and ask a question, it's okay. Oh, and we have another one by Tom in the Q&A.
Okay.
Yes, I'm going to send a recording and the slides this afternoon. Okay, so that's done. Okay, well, I think we don't have any questions. Oh, no, one more.
Yes. Yes. The resistor layer does cover the whole. So it's a subtractive process. So when we put the resistor layer, it's on the entire copper. So so what happens is that when you do the first etch, we're going to remove a lot of the background resistor material, but the resistor material is still under the traces. So and so then you just open up on those traces where you want the resistor to be. But yes, it covers that whole one PCB layer, and then whatever you don't need as a resistor gets removed.
Great. Okay, thank you.
And because of that, one thing, because of that, the higher the resistor density, the more cost effective it becomes. So if you have a lot of resistors, the cost per resistor, as the number of resistors go up, the cost per resistor goes down. But in the case of the MEMS microphone, it definitely was a cost savings for them because of high resistor density. A lot of applications, it's not driven by the cost of replacing this resistor. That's really more performance, or if you can shrink the size of the board. So it's not going to be like a one-for-one, cost thing. It's really design specific.
Okay, great. Thank you very much, John. Oh, another one.
It turns out that the amount of what happens is we have products that have very low profile copper, and so we've tested up to 40 gigahertz, and the amount of additional loss you get because that resistive layer is so thin that the amount of loss you get is fractions of a decibel per inch in loss. So people are routing their high speed signals on those layers. In fact, we sell a lot of product to people using, PTFE, Teflon type, based materials use a lot of our material, and so they're routing high space, high signal trace speeds, on those layers. And the EM absorption application, I have a design note, Charles. So if you want to contact me, we have some examples of that. Where people are using as an EM absorber, like for our cards and other type of applications. It really comes down to the fact that designing those things are very much art as it is a science, as far as the patterns and stuff. Depending on the pattern is formed and the stack up of the material, you can get you can do a lot of manipulation of the frequencies that are that allowed to pass through and the ones that are reflected, and that can help you with that.
Okay, are we done? Seems like we are. Great, thank you so much everyone for attending. Thank you so much, John and Amit, for presenting. It was really great to do this first webinar with you on this topic. I will send everyone the slides and recording this afternoon, and I wish you a good day.
Yeah, thank you again for having me, and I hope everybody learned something. And again, appreciate your time, and I know everyone's very busy. And please reach out to us with any questions.
Thank you, everyone. Thank you, John. Bye-bye.
Thanks, John. Thanks, Lucy.
Thank you very
Thanks.
much.
Thanks, Vandana. Thanks, Steve.
Thank you. Bye.